Hello everyone and welcome to Everyday Lead Code. This is Tej Doshi and today we are going to solve a very interesting problem, that is lowest common ancestor of a binary tree. Now it's a very uh, it's when you think about it, it's a little difficult, but when you solve the problem, it seems to be easier than you think. So let's just first understand what is the problem. The problem is you are given a binary tree. It's not necessarily a binary search tree, it's just a binary tree, and you need to find, and you are given two nodes whose lowest common ancestor is supposed to be found out by you. Now what happens is, so for example, they have given this particular binary tree. If you observe this binary tree here, and in the first example, p is equal to 5 and q is equal to 1, so the lowest common ancestor for these two would be a 3. So you output a 3. You output the node exactly, but yeah. Anyways, then you have, if what if you had a 0 and a 6, then the lowest common ancestor would have been a 3. The If you observe, if you had a 4 and a 6, the lowest common ancestor would have been a 5. So if you see, the lowest common ancestor 5, okay, if you are at this particular root in your recursion, and in the left subtree you find a 6 here, and then you find a 4 on the right side, then that means 5 is the lowest common ancestor, right? So similarly, if you had a 0 and an 8, you found a 0 and you found an 8 on the right subtree, then that means 1 is the ancestor. So what we do is we generally take single node, and then with respect to the single node we think about our recursion. So if, for example, okay, the single node I take, let's just say that 3 is one node. There is a binary tree like this: 3 5, hold on, or 1 is here, a left subtree, the left child of 5 would be maybe a 3, again 2 maybe. I can keep this child as, what can I keep, 3 or 4? 4, if I keep, uh, I can keep this child as 11 maybe. I'm just keeping it here. I can keep this child as 20, just so yeah, I just need to make it a little clearer in terms of this. Yeah, so this is the left child, this is your binary tree. Yeah, imagine there are, yep, so imagine this is the 5 is the left child of 3, 1 is the right child of 3, 2 and 4 are the left and the right child of 5, and 1, 11 and 20 are the left and the right child of 1. So now let's go about it. uh, Given 4 and 1, which is the lowest common ancestor, it's 3. Given 11 and 20, which is the lowest common ancestor, 1. Given 2 and 11, which is the lowest common ancestor, 3. So we observe something, right? So what we can do is we can simply keep moving down on the, so on the left subtree, we keep moving down 3, then we move to a 2, and so on. Now after that you move to a null, so you return back, you go here. It's normal post order traversal. Now you return here, then you go to the right subtree of this guy, and so on. Okay, so we observe that if you had a single node, and if you find p in the left and q in the right, then that single node is going to be your lowest common ancestor, because the recursion is moving from down, right? That's the reason you do this. Now let's In fact, let's just walk through a code. Okay, if you had a single node and if that node would have been a null, that means that there is no lowest common ancestor and you return a null. If your root itself was a p and or a q, then the lowest common ancestor would have been a p or a q, definitely, uh, because I'm going from up to down when I'm moving downwards, right? Then I search the, let's say if these cases are not present, then I search the left subtree and the right subtree. When I search the left subtree and the right subtree, and if let's say I did not find p or a q in the left subtree, and I found a p or a q in the right subtree, then I will return that particular node as the lowest common ancestor. So for example, let's walk through an example rather than just going about this. Let's just take the example that is given here, and let's take the second example. P is equal to 5 and Q is equal to 4. So now this is my tree. Imagine this to be your tree. Oops. Let's go back. Lowest common ancestor of binary tree. Oh, it took some time. So yeah, it's a, okay. So imagine this is your tree. 3516208 whatever, blah blah blah. P is equal to 5. I go, initially my pointer is at the root. I go, and since it's not a null, since the root is not null, the root is not equal to p, neither it is equal to a q. I do not do anything. I say the new root, call the lowest common ancestor, such that this becomes the new root. So 5 becomes the new root. So I'll just make a call stack here. Okay, I'll write root is equal to 3 initially. Now the function goes to root is equal to 5. When the root is equal to 5, what happens? It checks if it's a null. Is it a null? It's not a null. Is it equal to a p or a q? Yes, it is equal to a p or a q. So it returns that particular value to 3. So my left search, so left search variable will get a 5 over here. Okay, now what happens to the right search variable? Now you start searching towards the right. Okay, this is my call stack. Now call stack, now I search towards the right, so root becomes equal to 1 initially. When root is equal to 1, is it equal to a null? No, it's not a null. Is it equal to a p or a q? It's not equal to a p or a q. Then you then you go to the left of that particular root. So your call stack becomes root is equal to 0. Okay. Is it a null? No, it's not a null. Is it p or q? No. Then you still search the left. Still search the left. Okay. Root is equal to a null now. The moment root becomes equal to a null, what happens? It returns a null pointer. So the when it returns a null pointer in the left search of this guy, I will get a null pointer. So I move ahead. I move ahead. It's a right search. Right search also, it returns a null pointer. Even the right search returns null pointer. Now both of these return a null pointer. So even over here, the left search one, okay, one's left search would return a null pointer. I'm not sure about this thing. Then it searches the root becomes equal to 8. Root becomes equal to 8. Its left search and right search, both of them will return a null pointer. And the right search will also return a null pointer. So that is why there would be a null pointer on 1. right search would be equal to null pointer. So it returns a null pointer to the right search of root was 3. So left search is a 5 and right search is a null pointer. Then it means that is to say that uh, left search is 5, right search is a null pointer, and that is why I would say that uh, what happens, left search is the lowest common ancestor, lowest common ancestor here. So that's how you walk through this particular code, and this is how you solve it. You just take one node. You know that if both of these are, if both of them, if you have a root over here and the left subtree contains it contains p and the right subtree contains a q, then that is the lowest common ancestor. You return that. Else what happens is, um, if the right subtree returns a null, but in the left subtree, it means that both of these numbers, if they are present, they have to be in the left subtree. So you go search the left subtree, find the first one, first p, and then you just return that particular p. So that's how you solve this problem. It's a very, very simple problem. uh, it's just that recursion, you should make a call stack whenever you do any recursion. uh, it will help, and it will help your understanding grow. So that's it for today. Have a great day.